Yeah. Um, Thanks for hitting the record. Um,
Yeah, I just started the recording, Daniel.
cool. And I think we are good to go. So, Mansi, please take it away.
Thank you so much. Hello, everyone. I'm really excited to be talking to you today. My talk is titled Bridging the Discrete-to-Continuous Data Divide in Scientific Machine Learning. And so, without further ado, we'll dive right into our motivating applications. I'm told I'm speaking to a room full of mathematicians, and so I know many of you must be interested in modeling physical phenomena. And we know that partial differential equations describe the physical world. And so, in order to model this physical phenomenon computationally, we need to do a couple of interesting things. Before we dive into our talk, I'm going to highlight a couple of applications such as climate, weather, blood flow, turbulent flight, and heat transfer. And even though these are really diverse modeling applications, something that they all have in common is that the resolution at which these applications are modeled at is really important. So not only are we interested in modeling physical phenomenon, we are interested in modeling phenomenon which is in real life continuous in a discrete fashion. So to motivate this point a little bit, on the screen, I have two side-by-side simulations of the same turbulent fluid flow. And what I've highlighted in pink is a region of this fluid flow in which, in the low resolution simulation, we've lost some detail. And so this question of how coarse or fine your resolution of your simulation is one that is usually left up to the scientists doing their study. And the answer to this question can inform things like how safe or applicable your simulation is. So take, for example, the application of modeling turbulent fluid flow around an airplane. You really want fine-grained details to be resolved accurately. And so to talk about how we handle the problem of selecting the appropriate resolution in our simulation workflows, I'm going to get everyone on the same page with highlighting what a traditional numerical modeling workflow typically looks like. And so this is a very simplified version, but what typically happens in the beginning is a scientist or a mathematician specifies some sort of initial conditions. So in this case, I'm interested in modeling a 2D heat equation, and my initial conditions are over a square with two initial heat sources. You run some sort of a numerical method forward in time, and you repeat it n times steps. And so in this case, I believe this is a simple finite difference scheme that I've coded up. What is interesting to note here, though, is that the numerical method step, querying it, is really expensive. And the cost of querying the numerical method actually scales with the resolution at which you're doing the simulation. And we know from our previous slides that querying our scientific simulation in fine detail is really important. Resolution plays a huge role in a number of downstream applications. And so traditional simulation software has come up with a solution, almost an entire subfield called adaptive mesh refinement. And so to get everyone on the same page about what adaptive mesh refinement is it's a question one asks about how and where to allocate compute during your numerical simulation. So for the example on the screen here, we have a simulation of turbulent fluid flow. And the difference between what I showed earlier and now is that now we have allocated compute differently depending on where we are spatiotemporally in our simulation. So the areas immediately around the airplane are resolved in finer detail than the areas further away from our airplane. And that makes a lot of sense because those areas closer to the airplane are probably where we're going to get turbulent mixing, and they're more impactful to the safety of our application. And so we know that resolution plays a huge role in accurately modeling scientific systems, and that cost is a key consideration. And because of this, increasingly, typical schemes to mitigate cost, even things like adaptive mesh refinement, can still be very expensive. And so increasingly, we're seeing that machine learning is starting to make its way into these workflows. And so concretely, what is the role of machine learning? Um, what it can look like is instead of running a numerical method forward in time, you simply replace it with a set of pre-trained neural network parameters. And what this gives us is a workflow in which model development is decoupled from model deployment. And notably, what this means is that the deployment of the model is now substantially cheaper than querying a numerical method over and over again. But I know that we have cheaper forward inference of our neural network, but there's still a lot that goes into developing that neural network in the first place. So let's break down that workflow a little bit more. The first step in developing your neural network is typically generating data with which you will train your neural network. And interestingly, this is oftentimes in practice done via querying a training a neural network. And so this is typically done by querying a numerical method. The next step is you take the data that you've generated to train your neural network. And of course, if you have experimental data, you can also use that at this point. And the third step is you deploy your neural network for inference. And of course, we're interested in costs in this machine learning pipeline. The one good thing we know is that model development costs in step 1 and 2 is amortized over the lifetime of your neural network. So what this concretely means is that if you've done a good job of training your neural network parameters, then you can, in theory, use your neural network parameters for a really long time, and that upfront cost you incurred for data generation and training trivializes over the lifetime of the model. But what is still key is that resolution is still the driving factor for computational cost in this workflow. In step 1, the cost of generating data scales with the resolution at which it's generated. And in step 2, the cost of training over the data also scales with resolution. And so this is interesting and perhaps a bit of a dilemma because we know that cost is what motivated neural network integration into these computational simulation workflows in the first place. And so the fact that steps 1 and 2 are expensive is no small thing. And people have started to come up with methods to work around that limitation. And so one thing that has been proposed in this literature is this workflow called zero-shot super resolution. And so put simply, what this workflow aims to do is it aims to cheapen steps 1 and 2 in this workflow by reducing the resolution of the data you're generating and training over, and then enabling your neural network, your trained neural network, to then be deployed at inference time at arbitrary resolution. And so that's what we're going to be studying in this work. We're really interested in understanding the trade-offs that happen when you attempt to reconcile computational cost versus downstream machine learning performance. And so just to get everyone on the same page with respect to lingo, zero shot is just an ML term that oftentimes means querying a neural network without that data being in its training set. And so concretely, the act of doing zero-shot super resolution is when you're querying a neural network that was trained at low resolution to do inference at high resolution. This zero-shot super resolution workflow is actually a working claim that has been proposed in several recent papers, and it's a growing body of work. And so concretely, our thesis question in this talk is going to be, can neural networks trained on low-resolution data accurately resolve details in high-resolution data at inference time? And remember, this is an important question because resolving details in high-resolution data is a safety-critical requirement. And so in order to answer our thesis question, I'm going to get everyone on the same page with respect to some signal processing background. I know I'm talking to a room full of mathematicians, but hopefully we're all on the same page. So I'm going to introduce the Whittaker-Shannon-Nyquist theorem. So this comes from the seminal paper, Communication in the Presence of Noise, written by Claude Shannon. It's an age-old theorem, and it goes, if a function f contains no frequencies higher than w, it is completely determined by giving its ordinates at a series of points spaced 1.5 w seconds apart. And something I thought that was really funny in this paper was this line that came after the theorem. This is a fact, which is common knowledge in the communication art. So Claude Shannon thought this was a really obvious point. But just to break down this theorem in plain terms, what it means is that the sampling rate that you're attempting to measure your system at must be greater than at least 2 times the largest frequency you're hoping to accurately measure in your system. Another rephrasing is that this thing called a Nyquist limit is always the floor of half your sampling rate, or in other words, the Nyquist limit is the highest measurable frequency in your system, accurately measurable frequency. And so I'm going to make the Shannon-Nyquist theorem very concrete on this slide, and I'm going to lead with a 1D example. So let's say I have prior knowledge of a system and I'm attempting to measure it. My system is this underlying blue dotted curve, and I know that the underlying frequency of that is 7. So by the Whittaker-Shannon-Nyquist theorem, I know that my sampling frequency must be at least double my signal frequency. And so I choose a sufficiently high frequency at 20, gives me plenty of extra room. And I know that I am accurately measuring my underlying signal. You can verify that I'm making the accurate measurement by looking at this curve called an energy spectrum. And what an energy spectrum tells us is basically how much mass there is in your signal at every frequency that you're able to measure in your system. And once again, how do you know how many frequencies you're able to accurately measure in your system? Well, that's given to us by our Nyquist limit. And so we know we sampled our system at frequency 20, and so our Nyquist limit is half of 20 or 10. So we know that we can accurately resolve up to 10 frequencies in our system. And we see, as we expect, there's a spike in energy or there's extra mass in the energy spectra at frequency bin 7. What happens if you don't obey the Whittaker-Shannon-Nyquist theorem, however? So again, this is a scenario in which I have prior knowledge about our system. I know that the signal frequency is 7. So if I choose a sampling rate that's too slow, so not greater than double that, so a sampling frequency of 8, I run the risk of actually measuring the wrong signal or thinking I've measured the wrong signal. So to make this concrete, what has happened is because I'm sampling at a frequency limit of 8, the Nyquist limit is actually half of that, so 4. We can only measure up to 4 frequencies in our system. And what has happened is that that original spike in energy that we were seeing at frequency 7 has actually wrapped itself around that Nyquist limit, and now we're seeing a spike in energy at 1. And this is incorrect. We have incorrectly measured our system. And so how do we measure our signals correctly in settings where we don't have prior knowledge of the system? So we can't calibrate our sampling frequency perfectly. Well, I'm going to lead with a slightly more complicated example here. It's a similar, system, but instead of one underlying frequency, we have 2 underlying frequencies, 2 and 7. And so I've measured my underlying system sufficiently with a sample frequency of 20. And so we're seeing that we're accurately getting a spike in energy at signal frequency 2 and at signal frequency 7. And we know this is accurate. We know that we have the limit to sample both of these because our Nyquist limit in this setting is 10. Now, what happens if I don't actually know what our greatest frequency in our system is? So if I don't know that the biggest frequency in our system is 7, and I arbitrarily choose a sampling frequency of 10, what has happened is I've moved my Nyquist limit from 10 to 5. And what that means is that we still accurately measure signals that are under the Nyquist limit of 5. So we're getting a spike in energy at bin 2. But unfortunately, the spike in energy we should have seen at bin 7 now wraps itself around the Nyquist limit and manifests at bin 3. And so, like I said before, this is a setting in which maybe you don't have prior knowledge and you don't know exactly how high to set your sampling frequency. So what can you do about this? One solution is if you have a limit on how fast you can sample the system, maybe you can't afford to sample it more than 10 times a second, you can use that knowledge up front to set a low-pass filter on your system. So here we know the Nyquist limit is 5. We can accurately measure up to 5 frequencies in our system. And so I'm going to limit up front our system to only contain the top 4 frequencies, just to be safe. And by doing that, I've tossed out any frequency information higher than 4. And so what happens when I go to measure our system at sampling frequency 10 is that I accurately resolve the signal at 2, and we don't have any extra wrapped around information about frequency 7. And so I've been explaining the Shannon-Nyquist theorem in terms of these 1D signals, but what is the implication of this in a real 2D setting? So take, for example, you're trying to measure a system, like a scene of a zebra that contains high frequency information. In other words, the stripes on the zebra. And let's say that your camera or your sampling resolution is changing. If you're not able to resolve the system in a sufficiently high sampling rate, what you end up risking is measuring the wrong thing. So your zebra ends up looking a bit like a cow. If you know upfront, however, what your limits on your sampling rate are, you can afford to actually put in a low-pass filter preemptively, and now what you get in the bottom row is a much more blurry but much more faithful representation of your zebra at all 4 resolutions here. So I think it's a really nice illustrative example, and I've borrowed it from an open source MIT course. And so if anyone's interested in brushing up on their signal processing background, I highly recommend that link. And so now that we know what the Whittaker-Shannon-Nyquist theorem states, how do we connect it back to our machine learning computational science workflow? Well, to remind us, we all need machine learning models that can be inferenced at multiple resolutions. And equipped with our knowledge about signal processing, we know that new resolutions means new frequency information being introduced into the system due to an updated sampling rate. And so we're going to ask the question, what does this knowledge mean in the context of a zero-shot super resolution workflow? And I'm going to illustrate this question concretely through an example in which I'm attempting to model Darcy flow, or it's a laminar fluid flow data set. And so what happens if we train a model on a low resolution data set, like the one on the left-hand side of the screen? This is 16 by 16, and which means our data set only has up to 8 frequencies in it. And then I attempt to use that trained model on a data set like the one on the right, which is 128 by 128. And there's far greater frequency bins in our system, up to 64. And so I'm going to get right to it. These are our results. So this is an example of a prediction that a model made on 16 by 16 data. This is very similar to our training distribution. We get a blurry image as to be expected at this resolution. And what we're really interested in is assessing if the model, the neural network, is correctly allocating energy across the frequencies that are available in this image. And we do that by comparing the model's predicted spectra to the ground truth spectra. And so in that middle row, what we're seeing is that both of those lines are closely overlapping one another. And that's a good thing. We can also see another version of that plot in the bottom row, which is simply the difference between the model prediction spectra and the ground truth spectra normalized by the ground truth spectra. So that's telling you how much error there is at each frequency. And we want error to be low, so as close to 0 as possible. And so we're getting pretty low error, and that's good. But as we diverge our resolution at test time from what the model was trained on, we start to see a slightly different story. We start to see that the model's prediction spectra are starting to diverge from the expected ground truth spectra. And notably, this divergence starts to begin around frequency 8 in every single one of our increasing resolutions. And knowing what we know about the Nyquist-Shannon theorem, this isn't necessarily surprising because we know the model's training distribution only contained frequency information up to frequency 8. And so what this may manifest in is predictions that contain some high artifact noise. So we're interested in this talk in understanding, why does this behavior happen? And in order to answer that question, we revisit a core tenet of machine learning research. We know that out-of-distribution data is typically bad at inference time. And so we have this thesis question: can neural networks trained on low-resolution data accurately resolve details in high-resolution data at inference time? And knowing what we just saw in the previous slide, we form this hypothesis that changing the resolution between train and test time is akin to out-of-distribution inference. But how do we test this hypothesis? So I propose in this paper to break down the behavior of super resolution into 2 concrete workflows. And I'm going to illustrate that workflow in our simple 1D setting first, and then translate it to neural network inference. So let's say we have an underlying system. We know its signal frequency is 3, and we've sampled at a sufficiently high frequency of 40. The first behavior we're interested in is the behavior of interpolation. So we say a system can interpolate accurately if it can resolve intermediate points between those points that have already been mapped. So in this case, the underlying frequency information has been held constant, but what has happened is we've interpolated between the points we've already measured accurately. The next behavior we're interested in assessing is the behavior of extrapolation. So in this case, if you're comparing setting A to C, what has happened is the frequency information has increased, but the underlying sampling rate has not changed. So what we're hoping is if a system can extrapolate, it can accurately resolve new frequency information without changing its sampling rate. And so we argue that these 2 behaviors put together is what constitutes the behavior of super resolution, which is when new frequency information has been introduced into your system, and the resolution at which your system is being queried has also increased. And we make the argument that if a system can't interpolate and extrapolate, it definitely isn't super resolving anything, and potentially instead, it's aliasing. And so here I've defined super resolution in terms of sampling rate, but how does this translate to neural network inference? In particular, I'm going to assess a trained neural network's ability to both interpolate and extrapolate independent of one another. So let's start with some resolution interpolation experiments. And just to help the viewer keep these experiments straight, I've posted the sample of what it looks like to do interpolation in 1D in the top right-hand corner of this screen. But concretely, just in writing, we're interested in assessing if a trained neural network can generalize to new changing resolutions under constant frequency information. So what this experiment looks like is you train your neural network at a fixed resolution, in this case 16 by 16. We know that the frequency information in a 16 by 16 image is at max 0 through 8 frequencies. And then we go ahead and test our neural network on different sized inputs of the same image, but with constant frequency information. So what we've done here is we've increased the resolution of our our test set, but we've applied a low pass filter at limit 8 to make sure we're only seeing the top 8 frequencies in all 4 of these test distributions. And so when we do our experiment with our trained neural network to see how it performs, these are the results we get. And I'm going to explain the metrics you're looking at here. The y-axis shows the normalized residuals of the model's predicted energy spectra. So to remind ourselves what that means is the difference between the spectra of what the model predicted from what we expected the model to predict, normalized by what we expected the model to predict. And what we're observing is the model tends to predict higher energy in the frequencies, the higher frequency range. And this is error, this is erroneous. This result seems to suggest that neural networks are not capable out of the box of interpolating to new resolutions. In light of this, we are now interested in assessing a trained neural network's ability to generalize in the setting of information extrapolation. So once again, I have pasted an example of what it means to do information extrapolation in the top right-hand corner. And in English, what I mean in this experiment is that we hold the resolution of our test data constant, but we slowly introduce new frequency information into our test sets. And we assess a neural network's ability to generalize in this setting. So what the training distribution of this neural network might look like is a 128 by 128 image, but one in which we've filtered out everything but the first 8 frequency bands using a low pass filter. And then at test time, we slowly increase the amount of frequency information we allow into our system by relaxing the limit on our low pass filter. And then we test our trained neural network's ability to do inference at all of these 4 settings. And just like before, these are our results. So we're plotting the normalized residual energy on the y-axis here, and we're assessing the amount of incorrectly allocated energy at each of our different frequencies. And so like before, what we're seeing is the model is incorrectly predicting high amounts of energy in the high frequency range. This suggests a failure to generalize. Specifically, neural networks don't seem to be able to extrapolate new frequency information at test time compared to what they were trained on. And so we return to our original hypothesis, armed with the knowledge that neural networks struggle with out-of-distribution inference. We now know that changing resolution between train and test time is out of distribution. And the sources of out of distribution in our system here are attributed to new sampling rates and new frequency information. So if we put both of these behaviors together, resolution interpolation and frequency extrapolation, we get the behavior of zero-shot super resolution. And so here I concretely assess a neural network that is trained on an incompressible Navier-Stokes turbulent fluid flow dataset. And I assess if a model trained at resolution 255 can generalize to settings of resolution 510 and even resolutions lower at 128. And what we concretely see is actually a failure to generalize. We're noticing these like high frequency artifacts in both of these out of distribution resolutions. And even concretely in the predicted energy spectra, we see the model's predicted energy spectra usually allocates higher energy than is actually present in the ground truth of what the model should be predicting. And so equipped with this knowledge, it seems like instead of zero-shot super resolution, we might instead be observing aliasing. And if you've been listening closely, when I first introduced aliasing through the Whittaker-Shannon-Nyquist theorem, I introduced it in a data measurement context, and now I'm discussing it in a neural network inference context. And so there are some simple differences that I think are important to clarify. The first is the implication. If you incorrectly measure your data and you suspect aliasing, it means that you might have measured the wrong thing. So you're measuring maybe something that looks like spots instead of stripes. In neural network inference, humans are no longer interacting with the system, and instead the model may be predicting the wrong thing. It may be predicting the presence of energy in frequencies where there indeed is no energy. The medium of interaction has also changed in these two settings. In the data measurement setting, the medium of interaction is usually humans. We're sampling the real world via sampling instruments, and we have procedures to do this. In the neural network inference case, the medium of interaction is learned model parameters that have learned to interact with these representations through procedures like gradient descent. And so we know in the data measurement setting, if we're suspecting an aliasing issue, there are some simple solutions like changing your sampling rate, or if you can't afford to do that, employing low-pass filters. But in neural network inference, the solutions are less well studied. So what options do we have available to us to address this aliasing problem? On this slide, I want to highlight two potential solutions we investigated to resolve aliasing in the zero-shot super resolution pipeline. The first one is band-limited learning. And so the intuition in this workflow is that one can restrict the frequency space of both your training data and your inference data upfront. And so what that means in our experiment is we have pre-specified that the band limit of what we're interested in accurately modeling is 0 through 8. And then what I've done is I've employed two popular band-limited architectures, CROP and CNO, and we assess the CROP and CNO's ability to generalize across various training test resolutions. And so what we see is that at every single test resolution, we are accurately modeling the first 8 frequencies, but as soon as we pass the 8th frequency, our predicted spectra diverges from the ground truth spectra. So in practice, we're observing a loss of utility of both of these methods in a setting where we really want to be able to super resolve our underlying system. The next intuitive solution is physics-informed training. And I really liked this approach because we all know that physical laws don't change across resolution. What we found in practice and also concurrently in the literature is that physics-informed training objectives can be hard to optimize. It can actually make the loss landscape bumpier than it was without that objective. And so what that meant in our experiment is that despite a heavily tuned data and physics loss objective for our neural network ended up predicting less energy than there actually was in the system consistently across frequency bands compared to just a pure data loss. And so we know that aliasing is an issue in zero-shot super resolution workflows, but these two solutions haven't quite hit the mark for us. So we returned to our original workflow and asked the more fundamental question as to why are we attempting to do zero-shot super resolution in particular? So we revisit our initial guiding motivation. We know that cost was a motivating issue in neural network integration in simulation workflows. And because of this, the cost to develop the neural network in the first place was of significant importance. We knew that toggling the resolution that the model was trained at could significantly bring down the data generation and neural network training costs. But we found that this practice results in aliasing in step 3 at inference time. So what we do in our paper is we propose a simple data-driven technique to stem aliasing with multi-resolution training. What we advocate is that in step 1 during data generation, rather than generating all high-resolution data or all low-resolution data, you generate a mix of data. And what this enables is us to retain a lower model development cost because now you're able to balance the amount of high-cost samples you're generating with low-cost samples. And we would hope that this practice would keep costs low while enabling better multi-resolution test time generalization. So we check if our hypothesis is correct. We check if multi-resolution training does indeed enable better generalization. And we ask the question, how do we get the biggest bang for our buck? I'm going to explain a series of ablations we did to answer this question, but I'm going to start with just one ablation. So there's two factors we're interested in tracking. We want to track average data size because we know data size is what is correlated with cost, what drives costs in our system, which is the top row. And we know that we're also interested in model performance, which is test loss in the bottom row. So lower is better in both data size and test loss. And what I've done in this setting is I've created a dual resolution training data set. So I've mixed 50% of our data from resolution 64 and 50% of our data from resolution 128, visible in the middle row. And I've trained our neural network, and then I've assessed its test loss at 4 different resolutions. And unsurprisingly, what we're observing is that the test loss is lowest at the resolutions at which the model is actually trained on. We repeat this ablation combinatorially across the varying training resolutions. And what we see consistently is that you're able to toggle both the average data set size and the test loss by choosing which resolutions you choose to include in your training data set. So in this last column, I really liked it. It's illustrative. We have the cheapest data set size because we contain only 16 by 16 and 32 by 32 data, so relatively low res data samples. And we are unsurprisingly driving down test loss at those 2 resolutions, and we're sacrificing test loss at the greater resolutions. To the natural next question we asked is, well, if the resolutions in your training data govern the performance during test time, why not include a little bit of data from all of your test resolutions? And so we see that this indeed does work for us. By including 25% of our data from each of the 4 resolutions, we're achieving a medium dataset size, and we're achieving the lowest loss that we've seen so far on average across all 4 of our test resolutions. We ask if we can push the buck even a little further by actually creating imbalanced datasets. Datasets in which we contain mostly cheap, low-resolution data with a little bit of high-resolution data sprinkled in. And we see actually that we're able to achieve a pretty good trade-off. In particular, I like the example in the last column here. 95% of our training data in this experiment came from resolution 16 data, so super cheap. 3% came from 32 resolution, 2% came from 64, and 1% came from 128. And we see that while we are sacrificing a little bit of performance in terms of test loss at resolution 128, relatively the test losses are low. And if you look at our average dataset size, it's one of our smallest datasets to date. And so this was a really exciting result. And when we zoom out and do these experiments on a larger scale across 3 standard scientific machine learning datasets, we find that multi-resolution training enables Pareto optimal cost versus performance trade-offs. What we did in this experiment is we compared dual resolution training in the pastel dots to single resolution or zero-shot super resolution workflows in the red markers to multi-resolution training runs in the dark green markers. And what we're interested in here is our experimental points to be in this bottom left-hand corner. So what the y-axis is showing off is the average dataset size. And we know that dataset size is correlated with costs in our workflow, so we want lower dataset size. What the x-axis is showing is the average resolution across all 4 of our test sets, or sorry, average loss across all 4 of our test resolutions. And again, we want loss to be low as well. So we see consistently that multi-resolution training, a data-driven solution, enables this. I would like to highlight some impacts that this work has already had. We've seen the adoption of the spectral metrics we've proposed in several papers already. Multi-resolution training has been tried and tested in some external work and has already been integrated into a modeling workflow, which is exciting. And perhaps most exciting is that there have been several follow-up works that have began to characterize the limits of machine learning in continuous modeling workflows using some of the methodologies we've proposed. To summarize, I just wanted to paste a figure of a lot of the different methods that we've studied in this presentation so far. And I'm just going to conclude by reminding us of what we've learned. So we began this talk with the motivation that resolution is a key consideration in numerical modeling workflows. It can be really important to safely model things like turbulence, for example. And at the same time, we know that resolution is what drives costs in these workflows. Because of this, in machine learning, we know that a considerable amount of cost goes into developing neural networks that then replace numerical methods in these computational modeling workflows. And so to drive down the costs of neural network development, zero-shot super resolution workflows have been proposed. Settings in which you train a model at low resolution and employ the model at high resolution. What we found through experiment is that zero-shot resolution is actually driving out of distribution inference, particularly as we start to diverge from what the model was trained on, the resolution. To think about how we can recover some of the performance of zero-shot resolution and stem the aliasing we're seeing, we investigated things like band-limited learning, which upfront pre-specifies the frequency range that we're interested in accurately modeling. But we find that by doing these pre-specified band limits, we end up sacrificing performance in the high frequency range, so it's limited utility in this super resolution workflow. Next, we consider physics-informed training constraints. And the reason we think these are a viable option is because physical laws don't change across resolution. But in practice, what we find is that physical constraints can be a little bit finicky to optimize and oftentimes underpredict energy in the frequencies of our system. And so we conclude that aliasing in the machine learning context is a data-driven problem, so we propose a data-driven solution. We propose multi-resolution training. And what we demonstrate is with multi-resolution training, using mostly low-resolution data and a little bit of high-quality, high-resolution data, you're able to achieve Pareto optimal cost versus performance benefits. And so looking forward, where do I see this work going? One thing that this work has highlighted is that we need better benchmarking. And so in the pipeline, we have some work in which we're attempting to treat neural network development a bit like canonical software engineering. For example, typical software engineering has notions of unit testing or, checking if something has gone wrong really fast. And so we're hoping to translate the same sort of paradigm into machine learning workflows. In particular, we have a collaboration climate science for this. Another issue is a lack of open source evaluations. So in an effort to advance this objective, on the next slide, I've released a series of resources with our paper that should enable this, and we continue to work on making large-scale evaluations available. The next interesting direction is continued methods development. We have some exciting work at the intersection of integrating machine learning with numerical modeling methods to get the best of both worlds. And perhaps what I'm most excited about is actually automated decision-making as we begin to integrate machine learning into computational science workflows. So in our work, there were many decisions that I made and that I assessed via ablations. So for example, I answered the question of how to select multi-resolution splits by doing ablations, but it would be really interesting to see if we could develop an online algorithm to make these decisions in real time, or even answer questions like, given n units of compute, how do you maximize the bang for your buck? How much compute do you allocate to training your model or developing data? And with that, I'm happy to wrap up. As promised, here are some resources. This work has been published at the International Conference on Learning Representations. I will be there in Brazil in 2 weeks. So if any folks in the audience are there, please stop by my poster. And please let me know if you guys are presenting anything as well. I'd love to stop by your work. And if you would like a one-stop shop to all of our resources, go ahead and scan that QR code. And in particular, I would like to highlight that on our GitHub, we have a Getting Started section in which we distill down every single one of our key experiments into a Jupyter notebook. So if any of these experiments were of particular interest to you, that's well-commented code. You're happy to take it. And if you have any questions, please email me. I'm online now or open a GitHub issue. Thank you so much.
Thanks, that was awesome. I'm just going to turn the computer around so you can see the audience for questions. Would you mind grabbing the lights?